Section 1.5, Uncertainty in Measurement. So now we're going to deal with numbers and the issue of how we report answers and numerical measurements, to be exact. And so we'll begin by considering what we call exact numbers versus inexact numbers. So exact numbers are counting numbers. So for example, if I count the number of people and I come up with the number 12, that's what we would call an exact number. There's no uncertainty, meaning it cannot be 12.1. That's not a possibility. 11.9 is not a possibility. It's got to be an integer value if we're counting them. So that would be an example of an exact number. Another example of an exact number are definitions. Let me actually get rid of this. We'll make a little room here. Are definitions. So there's certain defined numbers. 1 inch. You ever wonder, like, how do we decide what an inch is? You know, how do you know what an inch is? How do people decide that? Well, it turns out the inches these days, it's defined based on the centimeter. An inch is defined as exactly 2.54 centimeters. So no one would say it's 2.541 or 2.539. It's exactly 2.54. That's a definition. In the same way that 12 inches is 1 foot. That's a definitional value. It's not up for debate whether it's 12.1 inches is a foot or 0.99 feet is 12 inches. It's an exact value, and there's an agreement with that. Now, there are also what we call inexact numbers. And inexact numbers are essentially based on measurements, other than counting. So for example, if I measure the mass and I use a balance and it tells me, hey, it's 10 grams. Okay, that's how much mass that material has, 10 grams. Maybe it's a little ice cube or a big ice cube. But then I get a better balance. And I find out, hey, you know what? It's actually not 10 grams. It's actually 9.9 grams. The balance that I used here could only measure out grams to 1 unit, to one, the ones column. So it can either tell 9, 10, or 11, but it can't tell the difference between 9.5 and 10.5. It just rounds it to 10. But if I get a better balance, I might be able to actually figure out that, no, it's not actually 10, it's 9.9. And then I find an even better balance. I get one, get my hands on one, and it turns out it's 9.85, or no, 9.86 grams, let's put it that way. And you'd say, hey, it's not exactly 9.9, it's 9.86. And then we get an even better balance, and you find it's not actually 9.86, it's 9.858. Well, this leads you to an interesting aspect of the sciences, which is that if we have to measure something, we cannot know exactly what the value is. We can know it to amazing precision. So we might use the best balance in the world. I don't know how easy this would be to do, but suppose you had this, you put your engineers to work, and they found out that this was the mass. You'd say, that's amazing that you could measure it out that many digits. But we still wouldn't say that's the actual value. That's an approximation of what it is, because if I were able to make an even better balance, I might find out that it's actually not 8 here, it's 7, 9. And in even better balance, it's not 7, 9, it's 7, 8, 7. See what I'm getting at? That when we make measurements, we're really just approximating what the actual value is. There is no real value because the way we define a value is based on how well we can measure it. And there is no such thing as a perfect measurement. Everything down to the level of the atom is based on the energy of atoms vibrating and so forth and so on. And there's a certain amount of experimental error with that. So even if I could make a balance that could measure out the mass of something down to the nearest atom, I would still be approximating the value because I wouldn't know what the exact value of the mass of the atom is. So sometimes we get out of that by doing this. We say, hey, 2.54 centimeters is an inch. So we're not going to worry about measuring the inch perfectly. We're going to measure the centimeter as well as we can. But again, that's an experimental process. There is no actual perfect answer to that question. So those are called exact numbers. Now, why is this an important issue in the sciences? Why do people care about exact numbers versus inexact numbers? Well, it turns out we try to figure things out in the sciences. And if we're trying to figure out how much of something we're selling, for example, having a good understanding of how much we're selling is an important factor. So, for example, this is the famous old story. Suppose you have a piece of gold and you say, hey, that piece of gold is worth, $1,000. Now it has some value to it, right? Well, if I shave off a bit of it, and then I sell another one to someone at $1,000, and I shave a little bit after that, what happens is eventually, if I do enough of those, I'll have enough little shaved off pieces that I can make my own block. And I've taken $1,000 from those people, right? So how do we know whether we've shaved that off? We have to measure it, right? Well, how do we measure it? We have to use some kind of scale or a balance. So if that balance says, look, it's 15 grams, I might say, hey, wait a minute. How do I know it's not really 14.6 grams and you stole 0.4 grams to make your little block over here? I want you to use a better scale. I want you to tell me that that scale is not going to give me 15 or 16 or 17 grams. It's going to tell me, hey, it's 15 grams out to 4 digits past the decimal point, which is still not exact, of course, right? But at least it's a higher level of precision. So that's really what it comes down to. Imagine if you're talking about a drug and it's a very powerful drug. And I say, hey, take 200 milligrams of this drug. It's a very powerful drug. Well, suppose, in fact, my balance, which was used to measure 200 milligrams, could only measure out to the nearest hundreds. And in fact, it was really 242 milligrams. But it showed me that it was 200 because it can only measure out in the hundreds. Well, after a week of that, 7 days of that, and let's say they're doing it 2 times per day, that's an extra 42 milligrams times 14. That adds up to a lot of extra drug, right? And that might actually have some sort of adverse effect on the person. We're prescribing 200, but we're actually giving them 242, or maybe not enough, right? Maybe it's really only 163 milligrams. And so now what's happened is you're giving them not nearly enough over a period of time. So that's really, one of the issues as to why significant figures is an important issue. It has to do with confidence. How confident are we in the number that we have? So for example, if you go down to the store, and let's say you only have $1 bills in your pocket, in your wallet, or your purse. Okay, It's not likely you would do this, but it's just a little thought experiment. So you had all these ones, you didn't count them, and so you go in there and you find something, it's something you really want. Let's say it's an iPod. What's an iPod? Who knows? They used to exist. Okay, so you got some sort of device there, and they tell you it's $125. And you say, okay, they say, do you have enough money? And you say, well, I think so. Got this big stack of $1 bills. I think it's enough. Oh, well, what do you mean you think? Do you have $125 or do you not have $125? I think I do. There's some big stacks here, so it's somewhere around $125. But then suppose you go through and you count it, and you got 119. Now you might be able to bargain with the guy and get it down to 119, but you don't really have 125. So you really can't be confident in your assessment there unless you go through and count it, right? So it really has to do with this issue of confidence. How confident are we in the amount of money that we have? And that's all connected into how experiments are designed and the equipment that we use, that sort of thing. So that's why so much money goes into developing techniques. Now, sometimes when we make measurements, for example, let's say we're going to measure the length of something. And I say, hey, this is 2 centimeters. Someone might want to know, well, how close to 2 centimeters is it? We've already decided it can't be exactly 2 centimeters. It's a measurement. It can't be an exact value. You might say, well, it's 2 centimeters plus or minus 0.1 centimeters. This is a way of reporting what we call error, plus or minus. And what that means is you take the number, the measurement, and you subtract the error. So 2 minus 0.1 is 1.9. And then you add it, which is 2 plus 0.1, which is 2.1. And you report a range. And so what you're doing is you're telling people, yeah, I know it's not exactly 2. And here's the range. The range is it's anywhere between 1.9 and 2.1. And they say that's not good enough because I don't want one that's 2.1 and I don't want one that's 1.9. I want one that's 2. So you say, okay, I'm going to do a little bit better job and I'll make measurements a little bit better, and it's going to be more precise. It's 2 plus or minus 0.01 centimeters. So that means if you subtract it, you get what, 1.99? And you add it and you get 2.01. And you say it's somewhere between 1.99 and 2.01. And they might say, okay, that's actually close enough, because if it's off by 0.01 centimeters, that's okay with me. So that's acceptable. I'll accept that deal. Okay? So that's a way of reporting error. We usually don't do that in general chemistry. We don't report errors like that. If you take a more advanced chemistry series, like analytical chemistry or physical chemistry, you'll start looking at analyzing uncertainty in that sense. So the uncertainty there was 0.01. It's plus or minus 0.01. That's a way of reporting the uncertainty. So 2 centimeters plus or minus 0.1 centimeters. This is what we would call our uncertainty. That's essentially the idea here. So we're going to use a more primitive method in this course. It's simpler and it just uses some rules. And the first rule is what we do is we count sig figs. We count what are called significant figures. And significant figures is any number between 1 and 9 and then it's 0 if it's captive, 0 if it's trailing, and there's a decimal point in the number. So the decimal point is explicitly shown. and then 0 if it's trailing, and no decimal point shown. I'm going to put a question mark, meaning we don't know whether that counts as a significant figure. Okay, so let me show you what I mean by that. I'm going to show you a measurement in kilometers. Okay, so there's your measurement. All we're going to do is count number of sig figs. That's the first step, is counting sig figs. So here's what any number that's between 1 and 9 is considered significant. So this one is, this one is, this one is, this one is, this is, this is. Doesn't matter anything, as long as it's between 1 and 9, it counts as a significant figure. If a 0 is captive, it counts as significant. Now, what do we mean by captive? Captive means it's in between numbers between 1 and 9. So both of these zeros are between numbers between 1 and 9, the 3 and the 2. So these ones would be considered significant. So this one would here, and these ones would here. Those are all significant. Trailing zeros. If there's a decimal point explicitly shown, it's a significant digit. So there's our decimal points shown. This one's at the end, it's trailing. So this one is significant. Now notice, what about these zeros in here? These are called leading zeros. These ones are not significant. So now that I think about it, there's really almost everything significant. It's just this right here, leading zeros are not. That's really the only one that definitely is not significant. If there's a 0 at the end and there's no decimal point in the number, it's unclear. It's hard to say. But if there are leading zeros, they're not significant. So these ones don't count. So if you wanted to count the number of significant figures in this number, you would count the 2, the 0, the 4, all the way to the 0 at the end. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This one has 11 significant figures. Some people call them digits. 11 significant figures or 11 significant digits. So you might ask, who cares? We'll get to the issue of why we care in a moment. Let me just show you a couple more. There's a number, 30,210. For those of you who use commas as decimal points, be careful. Here, comma means a placeholder for thousands and millions, powers of 1,000. Okay. The decimal point is where the difference between the ones column and the tens column. So here we go. We have the 3, the 2, and the 1. Those are definitely significant because they're between 1 and 9. There's a 0 here in between the 3 and the 2, so that's significant. Now, the only issue is this 0 at the end. There is no decimal point shown. So that tells us it could either be 4 significant figures, I'll abbreviate it Sig Figs, or 5. Okay? One way to ensure that it's significant, if you want people to know it's significant, is put the decimal point. Because if it has a decimal point and it's trailing 0, it's definitely significant. So this one would definitely have 5. That gets rid of any ambiguity. Okay? So there you go. Now, counting sig figs. The next step is the rules of addition and subtraction. I'll just write plus or minus addition and subtraction. If you are adding or subtracting numbers, what I recommend, most authors would recommend, is you line the numbers up just like you learned in basic arithmetic. with the ones column on top of each other, with the decimals in the same column. And then you go through the arithmetic. And then you round. And here's the rule of addition and subtraction. You look for the number that goes the fewest places past the decimal point. So you see how this one only goes 2 places past the decimal point? 1, 2. This one goes 3. You find the one, you identify the one that goes the fewest, and you round to that particular column. In this case, it would be the hundreds column. So 102.731 would get rounded to 102.73 because this digit only goes out 2 places. Okay? Here's another example. 143.29 minus 20.1. Again, you line everything up. Do the arithmetic. 91.321. Then you round to the column that goes the fewest number of digits. This one only goes 1 digit past the decimal point. So we're going to round it here. So you look at the number that comes after it. If it's 5 or greater, you round it up. If it's below 5, you round it down. You truncate. So 123.2, right? Because 9 is 5 or greater, so you round it up to 123.2. So notice our answer only goes out the same number of digits as the one that went out the fewest in the measurement. These are measurements here. These are measurements here. Okay? Very simple. Now, what about multiplication, division? Multiplication and division. It's a slightly different rule. Let me show you. If you have 1.4 times 8.011, okay, these two measurements, you count the sig figs. This one has 2 sig figs. This one has 4 sig figs, right? See how this one has 4? The 0 counts because it's a captive. So then you calculate it out, 11.2154, and you count the one that has the fewest sig figs. That's this one. It only has 2. You round the answer to the same number. So if this one has 2 sig figs, you round this one to 2 sig figs. So you'd have 11. 2 sig figs. So see how the rules are different? Here you're counting the number of digits past the decimal point for addition and subtraction. But for multiplication and division, you're just counting the sig figs in each number and then rounding your answer to the one that has the fewest sig figs. This one right here has the fewest. So what about another measurement? What if you had 11.57 and then you were dividing that by 305.88? Okay, well you get 0.037825290964, right? That's a lot of sig figs. This is multiplication division, so you count sig figs. 1, 2, 3, 4. 1, 2, 3, 4, 5. So the answer gets rounded to 4. Now remember, leading zeros are never significant. So this 0 doesn't count. So this would be the first significant, that would be the second, this would be the third, and this would be the fourth. This one's 5 or greater, so you round it up. So it'd be 0.03783. And that would have 4 significant figures, and then you would have that one right there. Okay? That's essentially the issue. So the reason that we do this, the reason we go through these exercises, is because we want to report answers with a reasonable estimate of how well we know the answer. So like if I reported my answer here, that would be telling people that we're confident that we can measure this value all the way out to there. But that's unlikely. That would be an amazing, amazing experiment to measure all these digits. Think of it this way. Suppose that, get rid of the decimal point. Suppose it's 37825290964, and you were counting something. What is that, 37 billion? It'd be very unlikely you could measure something out to the nearest dollar. You may think that you could, but it would actually probably be very, very difficult to measure out 37 billion of anything down to the nearest one. However, if you look at this number, 3783, this one only has 4 sig figs. So now we're saying, look, it's 37,830,000,000, and we don't know what the other numbers are. It's unknown. That would be a more reasonable estimate. Okay? So in summary, counting sig figs, any number between 1 and 9, captive zeros, trailing zeros if there's a decimal point. If there is no decimal point, trailing zeros, it's not clear. If it's a leading zero, it's not significant. So you count sig figs. If you're doing addition subtraction, you line up the numbers and then round the answer to the nearest, to the value, to the same column of the one that goes out the fewest number of spaces past the decimal point. And then for multiplication division, you just pick the one that has the fewest sig figs, round your answer to that value. Now, one more thing I wanted to mention about sig figs is if you are doing a problem with multiple steps. Okay, so suppose I'm saying, look, 31.15 minus 2.12. And then you're going to take your answer, I'll call it x, and then you're going to take it and divide it by 15.015. And that gives you y. And then suppose in the next step, you take that value y and you multiply it by 31. And let's say that gives you z. When you do multiple steps, so that was 3 steps right there, don't round. Don't round. Only round at the last step. Okay, round at the last step only. If you round in intermediate steps, that leads to what are called rounding errors, and your answer could be a little bit too small than it is justified in being. Okay?